Hello and welcome everyone to an Applied Flow Technology webinar. My name is Nick Vastine. I'm a business applications engineer here with AFT, and today we're going to be going through an introduction to AFT Fathom. This webinar is ideal if you have no experience with our software and you're looking to build your first model. Maybe you're getting back into the software, maybe you're evaluating it as a prospective customer. Again, this will cover all of the basics that you need to know to build your first model and begin that analysis process. So first we'll touch on some of the assumptions and applications of AFT Fathom, brief introduction. Our first model will be a pump sizing example where we'll split it into two parts. First, how do we build the model? And then second, how do we analyze our system and the hydraulics behind our system? We'll touch on some other odds and ends, some convenience features that we include in the software, things like global edit and our heat transfer capabilities. And then to wrap up the webinar, we'll talk about some of the add-on modules which increase capabilities, add on other features to the base application. If you're looking to learn more about our product, again, whether as a user or as a prospect, we'll also touch on some other related resources. Obviously, the webinars, as you would have found, we have quite a few and act as a good learning path, but also we have written examples, training seminars, again, other pieces that we'll touch on. So brief introduction to AFT Fathom. Some of the engineering assumptions we're going to be dealing with is it's a steady state solver. So we're not looking at mass accumulation. Mass into the system should equal mass out of the system. If there's heat transfer in the system, again, it's a steady state representation of the model. We can use this steady state solver to approximate some long transients. We do that with the XTS module, again, which we'll touch on later in the presentation. The AFT Fathom solver is for incompressible flow. Most typically, that's going to be liquids, where the density of the fluid does not change dramatically with pressure. You can also apply these technologies or incompressible assumption to low velocity gases. As your velocities do increase with gases, or you want to capture those compressibility effects, how is your density of your gas changing as it flows through your system? You instead want to look at our complementary product, AFT Aero, which we too will touch on later in the presentation. AFT Fathom, while it is steady state and incompressible, it'll also consider transfer effects. So if you're looking at temperature delivery or ambient heat transfer, we'll touch on that again later in the presentation. And then also we consider non-Newtonian effects. So while most fluids are probably Newtonian, and in the case of Fathom, most systems are probably looking at water flowing through piping, we can also consider things like sludge or other materials from mining, for example. And again, whether that's a pseudoplastic or a dilatant, or we have some models for paper stock, all of those things can be considered within AFT Fathom solver. Some common applications, most common is looking at pump and system interaction. So we're looking at flow through these piping systems. Generally, we have a pump that is going to be driving our flow, and how are we going to lose pressure due to things like valves or orifices, other fittings and components that we want to capture. So considering pump system interaction, if we change our pump operation or if we change the system the pump is installed in, how can we capture that in our software? Efficiency studies, so with pumps and other equipment that require energy, how can we make sure they're operating as efficiently as possible, changing either the pump or the system operation? Troubleshooting is also very common. Let's say you have a physical system that's not working as you intend. You can build a model, understand what should be happening, then you can check for deviations and ideally identify those problems. In other cases, you may have an existing system and you're trying to expand on it, or you have components you're looking to replace. Again, building a model will confirm both the expansion capabilities and what equipment should be replaced first to, for example, improve efficiency, minimize energy going into the system. Some common systems, very common in the utilities. So cooling water systems, especially HVAC, district cooling, fire water, pipelines, injections, really anything that's going to have a liquid flowing through a pipe can be modeled in AFT Fathom. As such, it's always interesting working here and seeing all the range of different systems across a lot of different industries come in. And again, the hydraulics is going to be shared across all of those different systems. For context, here we see on the left a spray system. This is one of our example files if you're curious to build and analyze a spray style system. And this is sort of to demonstrate the complexity that these models can have. Obviously, as an introduction, we're going to be looking at a very simplified system, but all of these concepts will translate to more and more complex systems. So here we have the spray system where they could determine what pressure is required to meet a minimum flow rate through all of these sprays. This comes from a case study where they were looking at a cooling water system. We can see that they have their cold water supply marked in blue and their hot water supply or return lines marked in red. And I believe this was for a college campus or other larger distribution system, accounting for all those different consumers. And here we have another case study example. This was a 11-story HVAC system for data center cooling. So this was actually imported, which we'll also talk about later in the presentation. So again, that's our brief introduction. The main things I would remember is we're looking at primarily liquid systems in compressible flow at steady state. And in this case, we won't be looking at heat transfer or non-Newtonian effects. Instead, we're going to be focused on how is our pump going to operate in this system that we have created. So our first model is going to be a pump sizing operation. Here we have two reservoirs that we're trying to flow between. One is at a 10-foot elevation and the other increases 190 feet up. So we need to overcome that elevation change. That's what's called a static pressure increase or static head increase. And we're going to be flowing through about 1,000 feet of piping. That's what's going to introduce our frictional losses. So as flow goes through the pipes, it's interacting with the wall, creating additional frictional losses we have to overcome. In our case, we need to size this pump, and we're going to be sizing it for this 500 gallon per minute flow requirement. So we have 500 gallons per minute that we want to send from this lower tank up to this upper tank. Our fluid is going to be water at 70 degrees Fahrenheit. We'll touch on the different fluids available in our software. The pipe size is going to be ANSI steel with a 4-inch standard schedule. And in the context of the system, we're doing initial sizing of our equipment. We know our boundary conditions. We know the inlet conditions and the outlet conditions, but we don't know all of the fittings and losses that are going to connect this 1,000-foot pipeline. So if we wanted to consider things like elbows or isolation valves, check valves, things of that nature, we'd be able to capture that as fittings and losses within this pipeline. For now, we're going to estimate it, but we'll touch on how you can capture those fittings and losses in the software as well. So we'll be coming back to this drawing as we start building our model, and this will be, again, our introduction to AFT Fathom. So jumping over to the software now, here we're greeted by the startup window. So when you start up the application, this window comes up, where on the left, you can select models that you had previously opened for your convenience. Here in the middle, you can activate different modules, which again, we'll touch on later in the presentation. Select a working fluid. We have some different resources here on the right, whether that be quick starts, again, as a new user, if you're learning the basics of the software, different examples if you're learning specific features or particular systems, and then again, a range of other materials we'll get into towards the end of the presentation. One thing that I will touch on here is the modeling preferences, where we can set our units, language, interface, and default pipe materials. Here, if we click modify, we'll touch on kind of the unit flexibility of our software throughout the presentation. Here, I'm going to set my unit system to both sets of units. So we have both metric and US units available to us, and we're going to default to our US units. Here you can also say show all units or only common units. Here we'll show all units just to be as comprehensive as possible. So we'll remember those preferences, and then we'll begin building our model. Here we're working in Fathom 13, which is new in 2023. And these outline some of the new features that we've added here as well. So we'll hit OK. We'll make the software full screen. And now we're greeted by the first of what we call the 5 primary windows. So before we go any further, let's touch on some of the primary windows that we're going to be interacting with. The first is going to be the workspace. This is where we're going to draw the representation of our system, where we have our lower reservoir, our pump, our upper reservoir, and our connecting pipes. This is typically where you're going to do all of your model specification. And then we'll also come back to this to discuss workspace layers and how we can use that to review both model input and model output. The other piece that we'll touch on is model data. And both of these pieces are used to consider streamlining the model building process. So making the different junctions and pipes for our system, and then how can we double check our input through the model data tab. So if we jump back to the software, up here we see our workspace tab. This is the workspace primary window, and we have the model data tab, which is the, again, model data primary window. Our software is relatively intuitive. You can think of it as a drag and drop interface. So here we'll drag on our reservoir. This is going to act as our boundary condition. If you remember our 10-foot elevation tank where we're drawing our fluid from. We'll also add in a pump, and then we'll also add in our upper reservoir. We have plenty of other components that you can model. For example, heat exchangers, where if you enable heat transfer, you would see the various models, and we'll touch on that later in the presentation. You can also capture various types of losses. So for example, with valves, if you have the CV, KV, K factor, you can capture the specific pressure losses of that component. Other components for relief valves, for sprays, T's, both detailed considering their pressure losses and not, control valves. So all of these junctions can act as boundary conditions, sources of pressure, pressure loss, or can interact as the system evolves. So we've drawn on all of our junctions. We can now connect them with pipes. If I double click this pipe drawing tool, we can see that it maintains its selection, and I can very quickly connect my junctions. So you can see within a few seconds, we've drawn out our model. Now we have to perform our model definition. There's a few ways to check what we still need to define within our system, especially as your system grows in complexity. It can be challenging to manage all of those different objects. So if we click up here, where we can list our undefined objects, we can see we still need to add things for our pipe. So it still requires the length, the diameter, and the roughness. And for our reservoirs, we still require things like our surface elevation and our surface pressure. So this will be kind of, especially for a new user, good guidance to make sure that your model is fully defined, especially since you have to fully define the model before you can run it. So we'll close out of that, and we'll go through the model definition piece by piece. So to specify a reservoir or to specify any junction, we first double click the junction, which opens our properties window. Here we can change things like the name. Let's say it's the lower reservoir. And we can also specify things like our elevation, which was 10 feet, and our pipe depth, which was 10 feet. Here we're simulating an open tank, a tank open to the atmosphere, but if it was enclosed, you could also account for the liquid surface pressure. If we hit OK, we can now go to our upper reservoir, which again, we double click to open the properties window. We can rename it if we like. And here we can add our liquid surface elevation now of 200 feet and our pipe depth of 10 feet. These naming conventions are convenient, especially again, as your models get more and more complex because they're easily searchable. So if I wanted to find my upper reservoir, I can type that into the search bar up here. You can also log notes in each of these junctions. Let's say that you have a spec sheet and you're trying to log not only that I have a pump here, but here's the specific pump, here's when it was purchased, here's where it's designed to operate. All of that can be included in this notes field, and these two are searchable. So we've defined our two reservoirs. Let's further define our pump, where here we see we have quite a few more options. By default, we would model the pump on a pump curve. So if you're representing a physical pump, you could bring that information in, copy pasted from a data sheet. In our case, we're going to be sizing the pump to achieve the flow rate, where we want to achieve our 500 gallons per minute. We'll also set our surface elevation to 0, or the pump elevation to 0. One thing of note that I didn't mention before is all of the required input for the junctions, and as we'll see also for the pipes, is going to be highlighted in light blue. So as a new user, that's where your eye should go in terms of what needs to be defined to fully define your pump. If you're a more advanced user, you can also turn off the highlighting by double clicking up here, and that'll simplify the interface a bit. But again, as new users, as an introduction, I recommend leaving these aids on. So we'll click OK. We have our reservoirs defined and we have our pump defined. Let's briefly go back to our system to see what else we need to add. Again, we have our reservoirs and our pump. And now we have to add a 10-foot stretch of ANSI steel 4-inch piping, and then a 990-foot run of, again, 4-inch piping. Where here in our longer pipeline, we're going to add those additional losses. When we go into the pipe, here we can see some of the pipe materials are specified for us. If we wanted to, we could have a user specified pipe where we could say we have a 4-inch internal diameter, approximate an absolute roughness, and provide a length. And from the solver's perspective, this is everything that it needs to determine those frictional losses. However, from an engineering perspective, it's probably unrealistic that your pipe is exactly 4 inches in diameter. It may be reasonable for a very small system, but as your systems get bigger and bigger, those errors will compound and again can cause deviation from your intended design. One convenience thing that we include within our software is a range of pipe material databases. These are just standard pipe sizes built to a standard, so that way you can select them from dropdowns. You're standardizing your input, you're minimizing that introduced error by manually specifying things like your pipe diameter or your roughness. So here in our case, we're looking at ANSI steel, and we're going to set it to a size of 4 inches. Here, if we wanted to examine a different schedule, by default, we're looking at the standard schedule, and you would be able to see how that could change your inner diameter. Here, we'll stick with the standard schedule 40. It brings in a roughness for us where you could also add additional friction models. Let's say you have polished materials, or maybe it's more scaled and it's more roughed. You can include that as well. And any pipe material that you see here, if you have a material that we do not include within our default databases, you can always add that at a later time. So here, ANSI 4-inch length of 10 feet. We hit OK, that should be everything we need for our first pipe. And if we go into our second pipe, one convenience feature we include is that it'll bring over the previously used pipe size, assuming that you're going along your system. So that way, all I need to specify here is our pipe length. Again, as a reminder, the light blue highlighting is going to direct you to what is required specifications for each object. In the pipeline, we also want to consider all of the fittings and losses. Again, right now we're going to approximate them, but if we had more information, we could go to this fittings and losses tab, and here we can specify our fittings and losses. So within here, we include a few different sources for common losses. So here for bends, for example, we have 90-degree bends, 45-degree bends, whether they're threaded or mitered together. And let's say that we had 10 of these elbows within our system, it would provide a final K factor for us to consider. Similar to the pipe materials, you can also add your own fittings and losses. Let's say you have commonly accepted K factors, and in the same vein, you can add a specified quantity. So we have things like bends, valves, check valves, orifices. If you have area changes at the start or at the end of the pipe, that can all be folded in to simplify how your model looks on the workspace. So here we're going to add an additional K factor of 25, again, just as a representation of these different components because we're in this initial sizing phase. If we hit OK, we'll see that we now have this little icon indicating to us we do have fittings and losses within this pipe. And we'll also show that on the workspace with this little ampersand symbol indicating not only do you have the pipe frictional losses, there are other fittings and losses to consider within this pipe. So now we have everything defined for our model. We have our 2 reservoir junctions, our pump set to size at 500 gallons per minute, and we also have our piping set at 10 feet and 990 feet accordingly. If we wanted to review this input, we can go to the Model Data tab. And if I zoom in more so, This provides us at a glance a way to check what are all of our pipe lengths. Are we sure that they're all in consistent units? Are all of our pipe sizes consistent with one another? Similarly, we can check things like our pump and say that it's at 500 gallons per minute, which is what we're sizing for, and our reservoirs are at 10 feet and 200 feet respectively. So a common saying in modeling is garbage in equals garbage out. So making sure that your model input is valid before you start drawing conclusions from your results is definitely good practice. Anywhere that you see this kind of tabulated information, which we'll also see in output, you can also copy and paste into Excel if you needed to do additional calculations, or if you're having someone double check a model, if you wanted to, again, build on Excel, which that's sort of the nature of engineers. So we've looked at the workspace and the model data tab. Note, however, our model is not yet ready to run. If we were to click our run model, we can see we have this little stop sign. And down here in the lower right, we also have this status light, which is in red. So the last thing we need to define, if we go back to our drawing, is we have not yet defined the fluid that we are looking at. So here we want to examine our system for water at 70 degrees Fahrenheit. To specify our fluid, up here we have this fluids button. You can also access it from the analysis setup window, which we'll take a look at here in a moment. Where here we can also turn on our modules and also check are all of our pipes and junctions defined. The analysis setup window consolidated many different windows for model input into this one analysis setup area. Here we can see that anything with a green check mark is already good to go, and anything with a red exclamation point indicates we need further specification to run the model. So here we have not yet defined our fluid. And if you have the fluid information, let's say you're looking at water, and I believe it's 62.3 pounds per cubic feet, you could enter that here for your density, viscosity, and optionally your vapor pressure, but more likely you're working with a known fluid. And in those cases, we provide a few different fluid databases. For example, we include the AFT standard fluid database, which we've curve fit this information to work well with our solver. Here we have water, which we can specify at our 70 degrees Fahrenheit. And look at that, we get our 62.3 pounds per cubic feet. In more complex cases, maybe in oil and gas, you might have a mixture of fluids. By default, we include the NIST RefProp database, where you can create mixtures based on either mass fraction or mole fraction. Where here, let's say we were looking at an oil and gas system and we wanted to add octane, you could add those different components and again, represent what is the density and viscosity of my fluid going to be. Here we'll keep things simple, again, for the sake of our example, and stick with water at 70 degrees Fahrenheit. If you were to consider heat transfer, you could also implement that here, where you would enable heat transfer with energy balance. If you had various non-Newtonian behavior, you could select that again from the analysis setup window, whether that be paper stock, power law, Bingham Plastics, Herschel-Bulkley, or the homogeneous scale-up, which I believe is from more commonly in mining and dredging operations. Here we'll keep things simple with Newtonian, and again, looking at water. So with our fluid specified, we see our status light down here is in green, and we've removed that limitation on the run model. Our model is fully defined. If we click run, the last step will be to save our model. And now it's run, and we would be able to review our output. So before we go any further, let's briefly touch on the steps for building a model. Again, we saw how in the workspace, we connect all of our pipes and junctions and where we define all of the properties of our objects. Model data was very convenient for reviewing that input, checking things like lengths, units, as we get deeper and deeper into the software, seeing what is going to deviate between different scenarios, for example. And a common theme, again, with modeling, garbage in equals garbage out, so making sure that the input and building of the model is correct is essential. While we went ahead and built our model, we could have alternatively imported our model from another file format, and that can save time and then also reduce input error, minimizing that redundant effort to rebuild a system. Here, this was a model from Navisworks, which was then imported into our application AFT Impulse. This is a surge analysis tool, but conceptually the same. You can import from these different file formats into our software to save yourself some time. AFT files can also be opened in other AFT applications. Let's say you're doing your steady state analysis in AFT Fathom, then you're tasked with doing a surge analysis for valve closures and pump trips. You'd be able to open that AFT Fathom model into AFT Impulse as well. In terms of the different options, you can import from PCF files, usually from CAD, Caesar2 neutral files, more common in stress analysis, GIS shape files, EPA-NET, and all of those are accessed from the file menu. So file, then import piping layout from, where you can select your file, you'll see a preview, and again, ideally will reduce some of the effort to import your system and begin your hydraulic study. We took a look at the different fluids. Again, for a custom fluid, we only require density and dynamic viscosity, but we can also model those predefined mixtures using either the built-in NIST RefProp database or the optional ChemPack database. We saw the range of non-Newtonian fluids that we can model. We'll also be able to capture those heat transfer effects, which can impact density and viscosity, which you can also apply to mixtures or user-specified fluids, depending on the information you're providing the software. And one thing I didn't touch on yet is you can also model different fluids in different pipes or sections of the model. So let's say you're modeling a process plant. Maybe you have your process fluid on one side, and then you're also modeling the cooling water loop on another side. We've seen some more unique applications. You can also model maybe a reaction or where the fluid changes within the system. One case study we had was a brine system where they were pumping brine, or I believe water, into a underground cavern, which was then returning brine. So they were able to model both segments of the system, considering things like the volume balance or mass balance across that cavern during steady state. Finally, we'll touch on libraries, which we saw when we were specifying our pipe materials. So whether that be a pipe material for ANSI steel or PVC or any other material, the range of diameters, schedules, and roughnesses. We saw all of the fittings and losses that you can add to your piping to consider those additional losses. The fluid databases and the fluid libraries that we have specified, where you can save your own user-specified data. Another thing you can do is if you have very common junctions, let's say you're using the same pipe or the same pump over and over across many different models or within the same system, you can save that to a library and it makes it very easy to call. And lastly, you can also save installations for heat transfer analysis. What's the conductivity of your fiberglass insulation, for example? As we saw, many of these are going to come predefined. So we provide a lot of pipe materials, fittings from Crane, Idlecheck, and Miller, fluids from NIST RefProp or from AFT Standard or from ChemPack. But in most cases, you can further customize it however you see fit. So if you're always coming back to the same pipe materials, odds are you're better off building a library, standardizing it across your team. You can host these different libraries on a network or share them among your team. They can be project specific or company-wide. And in general, investing in these libraries will help you standardize input. So everyone is using the same pipe sizes. That helps you reduce error because you're not manually entering anything. And then it's also going to save engineering time. You don't have to look elsewhere for those specifications. So this is really the summary of model building. We saw models are made up of objects, which we consider either pipes or junctions. Junctions can be pressure loss or pressure gain in the case of a pump. It could capture where fluids are going to be mixing within a model. So if you have multiple temperature streams, for example, where are they going to mix and what's your resulting temperature? And other junctions may react to changing system conditions. So in the case of pump system interaction, maybe you're operating elsewhere on your pump curve, maybe relief valves open or check valves slam. All of those things will be captured again as pipes and junctions within your model. We saw the workspace where we drew out our model using those pipes and junctions and making those connections. One thing I did not note is the model's arrangement does not impact your results except for how your objects are connected. So if we go back to the software for a moment and jump to the workspace, think of the workspace as a purely visual representation of your system. Here, if we remember, we have a 200-foot elevation change between this junction and this junction, but I could just as easily lower this junction all the way down here, rerun the model, and it's not going to change my output in any way. Or if we remember, this pipe is 990 feet, and this pipe is only 10 feet. If I run my model like this, again, I'm still going to get the same output results. So it's valuable to create a good visual representation of your model to kind of correspond to the system that you're representing. However, that's going to be defined by how you've entered your properties into each of the property windows, not necessarily by how are the objects oriented. We also took a look at model data, which is useful to double check our input or if we need to extract any information. And then there's quite a few ways to check what objects require further definition. So we saw here the show undefined objects, where here all of our objects are undefined. We also have this status light. So let's say in this pipe, if I were to delete our pipe length, here that'll indicate to us that this pipe still requires some input. And when we go back into it, add in our required pipe length, we'll see that the status is now good to go. Okay, so we've done everything to build our first model. Now let's see what the software is going to tell us. What information are we going to glean in this pipe sizing situation? We'll first take a look at our output, which is tabulated results. Again, this is useful if we need a specific number, if we're meeting a flow rate or pressure condition. It's also valuable because it'll indicate to the user if there's any problems within the model. So here, we believe we'll need to rerun our model, and we can go to the output using this output button. Here again, all of this tabulated information, if we wanted to extract it and do further analysis, you can copy and paste that directly into Excel. So here we're going to be looking at our pump summary, where here in pipe sizing, or in pump sizing, I should say, there's really two things required to size a pump. There's the flow rate that we require and the head that we require to generate that flow rate within our system. Those two pieces of information combined are our operating point, and that's what we would then take to our pump manufacturer. So as we saw, within only a few minutes, we can build a very simple system, size our pump, and we're off on our way. There's a lot of other information provided in output, things like volumetric flow rate, which you can imagine as your system starts to branch, you'll get different results, not just a single linear system. Things like velocity, which we could check, are we exceeding our velocity limits? Maybe we're getting excessively high pressure losses or erosion in our piping. And again, a range of other parameters as well. As I mentioned, one thing AFT prides itself on is unit flexibility. So let's say we are not in the United States and we're in anywhere else in the world, and we wanted to look at metric units instead. We can double click one of these parameters and we see this full range of different units we can pick from. So let's say instead meters per second. Now at a glance, we can see we're below 4 meters per second. We'll go ahead and correct this back to feet per second. And we can also change what parameters we show within this output. And we do that from what's called the output control window, which we can access from this button up here. And here we can see for our pipes, we see the volumetric flow rate that we have reported, our velocity we have reported, our static pressure maximum. And if we wanted to, we could change the units from here as well. Over here on the left, we have other parameters that you can use for your reporting. So let's say we wanted to show our velocity not only in feet per second, I can drag this up, and I can also show it in meters per second as well. So now I can see both of those units at the same time. I can customize this however I like. If I really don't care for how the static pressure changes compared to the pressure due to a change in elevation, maybe I can streamline this reporting a bit further as well. While you can export most of these parameters to Excel, in a lot of cases we most likely calculate that parameter for you. So it's as easy as adding it to your output through output control, and then you're provided that number directly. So we have that for pipes for different junctions. So changing what's reported down here, or our pump summary, if we wanted to look at our range of efficiencies or we were performing cavitation analysis, again, all of these parameters can be added through output control. So that's a high-level summary of output. You can further enhance it with output control. As we saw, we can add or remove different parameters and give you more unit flexibility. You can also do this analysis for multiple scenarios, which we'll touch on here later in the presentation. You can automate the export of this information to Excel, so you can create a template worksheet and then automatically bring out things like the flow rate and the DH of your pump or pump efficiency, again, streamlining that reporting process. You can also add what's called design alerts, which will automatically indicate if your parameter goes outside an acceptable criteria. So let's say we were looking at our velocity through our pipes and we had a 12 foot per second limit. If we were to add a design alert, it would automatically flag these two pipes and provide a warning saying, hey, you've exceeded your velocity restriction for these particular pipes. So a convenience feature that if you want to look into more, you can search design alerts, but for the sake of an introduction, for the sake of brevity, we won't go into detail here. In addition to output, you can also graph your results, whether that be a pump versus system curve, which we'll make once we get into scenarios, or profile graphs. So let's jump back over. And now we are on the fourth tab of the primary windows, the workspace, model data, output, and now graph results. Where here we'll look at a profile graph instead. Here we provide a wizard that will walk you through creating some of the graphs. So if you wanted quick and simple, you can select profile graphs and it'll give you some more instructions on how to create the graph. Here we're going to plot how our pressure is going to change along the length of our system. So if we click generate, we can see here how our pressure decreases slightly. We have our pump that adds a significant amount of pressure, and that erodes along the length of the pipe, both due to the elevation change and due to frictional losses. If we wanted to change the units, again, we have this unit drop down, or let's say we wanted to look at it in kPa instead. You can also add multiple variables. So with this add button here, let's say I wanted to show the velocity, which isn't the most exciting graph when there's only one pipe. And we can show both of these graphs stacked on top of one another. You can also show multiple variables on the same graph with this little right arrow to make a secondary y-axis. So velocity is selected. If we scoot it in, we can now see velocity here and our static pressure here. If we wanted to show dual units, we can also do that as well, selecting the same parameter. And here, let's say for kPa and PSIA. So now we have one plot, which can be convenient, especially if you're working internationally where you're familiar with PSIA, maybe your client is familiar with metric or vice versa. And again, those can be stacked on top of other graphs as well. So that is the profile graph. One thing you can do is save these graphs. So if you right click the graph and use add graph to list, I'll name this our profile graph. And now I would be able to reload this graph with the same parameters, any other changes I would have made to this template. And if I make any other changes to our system, let's say we want to do 600 gallons per minute instead. It's deleted all of our output. We've made the change to the system. We have to rerun our model. When we go to our graph results, we can very quickly reload that graph and see what's our new peak pressure, what's our new mass flow rate, for example. If you wanted to extract the information to Excel, you can also right-click, copy the XY data, and then you can paste that into Excel as well. So if you need more standardized graphs, though, I would recommend leaning into these graphs. We like to call them report-ready graphs, where you can copy the graph image and you can paste that directly into your report as well. So we can further enhance graphs. We saw dual y-axes. So if we have multiple variables or the same variable with different units, We didn't touch on multi-scenario graphing, which again, we'll touch on scenarios here in a moment. You can add annotations if you want to label different points in your graph, and then you can also customize the formatting. So we'll come back to graphs a little bit later to make our pump versus system curve, but the main bulk of it is using profile graphs to show different parameters and how they're changing, and then how you can save these graphs to then call them as you make further changes to your model. The last piece of analysis that we'll touch on in terms of the primary windows within our application is visual report, which is now becoming layers or workspace layers. So if you're using Fathom 12 or earlier, you would still be using the visual report, but all of those capabilities have now been folded into workspace layers. This provides us a way to display input or output data near all of the objects within the model. You can also create color maps that will color your piping to reflect the output. For example, here on the left, we're coloring based on the max static pressure, where we see much higher pressure in P2 than we do in P1. And you can also use it to control object visibility and style. So if I wanted to color code my cooling water system for all of my cold water supply and all of my hot water return, you would do that from the workspace layers. So here in Fathom 13, if you go to the visual report tab, we'll see it's now incorporated into workspace layers where you can review more documentation. And if we go to workspace, down here in the lower right, we can look at the workspace layers. So by default, we include one layer called the all objects layer. If I turn this off, the model still exists, however, we are hiding them. So if we wanted to, for example, isolate the cooling water system of our model, maybe we turn off all the other objects so that we can emphasize just that one piece of it. To demonstrate how it works, let's create a layer. So let's create a layer for our pipes. Generally, you should select the objects that you want to show input or output for. Then when you click this new layer button, we can create it from our workspace selections. So let's call it pipe input. So now in pipe input, we can see that we have our two pipes, which are included within the layer, and all of our junctions are not. Now, let's say we turn off our all objects layer, we can see we only have the pipes remaining because that's the only layer that's left visible. We'll turn all objects back on, and if we go back to our pipe input, here's also where we can change the style of the pipes. Let's say instead of gray, we wanted to make them red, or if we wanted to make them thicker. And again, we're making these changes only on this layer. So if I turn off this layer, we can see we're back to those default settings. So that's the change in style and visibility. From an output or kind of more engineering focused perspective, we can also add different pipe parameters. So here we can see, similar to our output control, all of these different parameters we can report on. So let's say we wanted to add our pipe length. And we can see when we add the parameter, it's added to our label here. If we wanted to also check our diameters, whether the hydraulic diameters, or we can check the nominal size. And now you can imagine with much larger models, it's very fast to go through and check, okay, all of my lengths are consistent, all of my nominal sizes are consistent with one another. So you can do something similar with junctions as well. Again, for the sake of brevity, we won't go beyond this kind of brief example. We'll show the color maps next, which again, we click new layer in color map. And here, let's look at our max pressure. And if we double click and open our color map, here we can see it defaulted to our maximum static pressure, but there's a number of different parameters that you can color your system based on. And here we can see it's provided us a range already. So for any pipes that are greater than 17 psi, but less than 57, we color those blue. Anything greater than 180, we color red. So as your model again gets more and more complex, hopefully you can see how you can color map your system to call out specific areas. If you wanted to change those parameters, you can also change those here, especially in cases where you have maybe you have a header with very high flow rate, and then you have all these very small branches. Maybe a more even distribution isn't the best way to represent your system. Maybe you have one very high one and then 4 very small ones, or you can add as many conditions as you would like. So that is the color map. Note that it overrides your style condition. So here it's no longer my red piping because we need to color it accordingly. But you can very quickly turn off your color map. You can turn off your reporting and get back to just the base model. So you can imagine if maybe I have all of my pipe input as a layer, I can quickly turn that off. Maybe I have all of my pressure responses as another layer, my flow rates. So that way, as you come back and forth, changing your model, seeing that cause and effect, you can very quickly turn on and off those different cases. And that is workspace layers in a nutshell. Some other applications. So if we wanted to check our model input and our output, as we saw, spot checking our lengths and our nominal sizes, you can screenshot these or print to a PDF to include in your engineering report. Makes it a lot easier to show I have these lengths of pipe rather than looking at my model data saying pipe 1 is length 10. Okay, that is the correct pipe. If you are doing that comparison, which sometimes is necessary, you can undock these windows and place them side by side. And you can also move these windows entirely off of your screen onto a second monitor. So quite a bit of convenience there as well. If you wanted to visually isolate your subsystems, let's say you were getting rid of all of the elbows that are kind of distracting within your system, or if you wanted to isolate only the cool water supply or maybe the flow path to a particular consumer, again, all of that can be captured with those workspace layers. And then as we saw, if we wanted to make multiple color maps or multiple layers for our pressure or our velocity reporting, again, you can lean into this capability as much as you like. You can turn on those reports on and off very quickly as you modify your model and come back to it. Next thing we'll touch on is scenarios. So scenarios are variations of our base system to quickly evaluate changes. So let's say, for example, we have a system like this where we have a supply that's going to tank A and tank B. In this case, maybe we only flow to tank A in some cases, we only flow to tank B in some cases, maybe we have multiple fluids that we're evaluating, maybe we even have different pipe sizes that we want to evaluate. So what you can do in our software is build out what's called a scenario tree so that you're accounting for all of those cases, making sure that whatever design considerations you're making, you have that sensitivity, you have that flexibility to analyze all those different cases. So these scenarios are duplicates of the models, and there are characteristics that your child scenarios will inherit from your parent scenarios. So, for example, here we'll go to our scenario manager, and we are in our base scenario. If you right-click the base scenario, you can create what's called a child scenario. And this is, again, an exact copy of our base case. So if we go to our output, we see we're still at 600 gallons per minute. You'd be able to run the same graphs. It's an exact copy of this base scenario. However, we can make any changes we want to this child scenario. We can clone our system if we want, and it won't modify this base scenario case. So if you put in a lot of effort calibrating, designing this base case, you can very quickly create a child scenario, change it however you'd like, and not worry about modifying or destroying the work that you've done so far. It also gives you a lot of flexibility because you can make other small changes to the system. Let's say that it's a pressurized system now instead. If I add 100 psi-G to this reservoir, again, that won't modify this same junction in the parent scenario. However, changes will permeate from parent down to child. Let's say in our pump, again, we're no longer looking at our 600 gallon per minute flow rate. We want to look at a 500 gallon per minute flow rate. If I click OK, changes will go from the parent down to the child, and we can see that it's now updated to that 500 gallon per minute flow rate requirement. Scenarios can be a lot to digest, especially if you like webinars. I would search for our Scenario Manager webinar, which goes through much more complex examples, but the more that you lean into scenarios, similar to workspace layers, the more that you're going to get out of the software. And again, we can very quickly delete a child scenario. We don't have to worry about it deleting any of our previous work. We can very quickly create a new child. So here, for example, let's look at adding a pump curve to our system. We've done our analysis. We've determined our operating point. We brought it to a manufacturer. We know we need 381 feet of head to generate 500 gallons per minute of flow. And now if we go into our pump, rather than sizing our pump, we can add in a pump curve. So here we'll enter our curve data. I have some information I've already saved, again, from Excel that we can paste in. If we generate our curve fit, we can see our head curve, our efficiency, which increases then decreases. That indicates our best efficiency point. And we can also consider our cavitation effects as well. So if we click OK, we've saved our pump property specification. And if we run our model, review our output, now we can see our results are slightly different. We're no longer fixing the system at 500 gallons per minute, and we see our pump is generating close to that 380.7 feet of head. If we wanted to compare, we could go back to our base scenario for our sizing. And here we can see where that pump is now operating on our pump curve instead. Again, scenarios, you can capture anything you'd like. So let's say we wanted to slow down our pump to 400 gallons per minute. If we go into the pump property window, we can go to variable speed. Say it's a controlled pump where now it's designed to set a 400 gallon per minute flow through our system. If we rerun our model, now we can see we have to decrease our speed to close to 90%. And again, we can create those child scenarios. We can test these different cases without worrying about destroying those parent scenarios. So the scenario manager, which is where we were creating those child scenarios and jumping between those different cases, it's going to manage all of those variations within one single model file. So if you need to make a change to a parent scenario, make other changes to child scenarios, or compare your input and results, all of that's captured within that scenario manager. And as I mentioned, there's no limit on what can be changed within a scenario. The sky is the limit. Use your creativity and curiosity as an engineer. Some other tools to manage scenarios. We won't go through all of these, but these are more to bring awareness. The first is the scenario comparison tool, where we could have these different cases and it'll indicate what's different between each of my scenario cases. So if you lean into the scenario manager and you get this messy scenario tree, this is an easy way to check, oh, this is what I'm testing in each of these cases. You can also isolate specific scenarios to files. That might be useful for sharing if you don't want to send them the full file with the full scenario tree. You can isolate a specific case. And you can also batch run different scenarios. So let's say I have all of these different cases I want to run. I can put them into a batch run and it'll run them sequentially. I don't need to babysit the solver, run it, wait for output, then run the next model. For further analyzing scenarios, we have multi-scenario output, where I could show all of these different cases all at the same time, looking at maybe what fails my design alert, my maximum velocity, or what's the most efficient for my pump operation. You can also do multi-scenario graphing to compare, for example, pumps in different systems. Maybe you're changing pump speed, maybe you're changing other conditions of your system. And also profile graphs. How is your velocity going to change? How is your pressure going to change across those different scenarios? You can also automate that reporting with Excel export, which you can access, I believe, from the file menu in output. To touch on the Excel integration a little bit more, we saw there's a few ways to copy paste information, whether you're copying it from output, model data, or copying your graph results. And you can also bring information into Fathom. We saw that copy and pasting our pump curve information in, but you can also do so for valve characteristics, your CV versus open percent, profiles of the pipe, and then also transient information if you're performing that analysis. So there's built-in integration for the Excel export manager, and then also Excel change sets to bring in information into the model. So that's a summary of our model analysis. So as we saw, we have tabular data, graphs, and then other ways we can color our system or bring that information directly next to the object. There's many ways to customize, whether that's adding and removing parameters or changing the units to suit your reporting. Scenarios, which I definitely recommend investing in if you're going to become a power user of the software. You can evaluate your design alternatives, operating cases, expansions, really anything that you want to check in a model. You can very quickly create a child scenario and build some tests. Finally, all of that analysis and reporting generally should be done within the software, but you can always extract that data to Excel or use Excel to mass modify your models. So that's really the bulk of building and analyzing your model. We'll touch on some odds and ends and some add-on capabilities as well. The first odd and end is a feature called Global Edit, where we can push one change to a collection of objects all at the same time. So in this example, let's say we have our original system with our 4-inch piping, and we want to change it to 3-inch piping. Now for 2 pipes, it might be trivial to go into each one and change it from 4 inches to 3 inches. Again, as your model becomes more and more complex, that becomes less and less practical. So to demonstrate, we can create a child scenario, create it from our base scenario, and let's say we want to look at our 3-inch piping. If we go back to our workspace, one feature I haven't touched on yet is the inspect feature, which you can hold right click to review different pipes. Here we can see it's still 4 inches, and if we check our second pipe, again, it's a 4-inch pipe. Global Edit, we can select the objects that we want to change. We can click this Global Edit button up here, and we can perform a global pipe edit. The functionality is going to be the same for modifying junctions as well as pipes, so the process is really similar. We're just going to be looking at a pipe in this example. Here we have our 2 pipes that we want to change, and we can select the pipe data that we want to modify. So here we can see very similar to just specifying our normal pipe properties. We have our pipe model, any fittings, insulation. If we wanted to add design alerts, we wanted to rename them. Again, any change that we want to push to our pipes, we can make from this window. So instead of a 4-inch pipe, I want to modify it to a 3-inch pipe. And if I click OK, here, these are the parameters that we want to push to our 2 selected pipes. So in our case, we want to push only the nominal size. We don't want to overwrite the length. We don't want to overwrite any other information. This is the one change we're making with this global edit. We can click Apply Selections, click OK. And now when we review our pipes, we can see they're both 3 inches in diameter. Again, not the most exciting example given only 2 pipes, but hopefully you can extrapolate out the power that this feature has. So note there's no limit to the number of objects or parameters that you can global edit. Any parameter that you can change from global edit, and even minor changes for 2 pipes or 3 pipes will be faster using global edit, saving you that redundancy. The next odd and end we'll touch on is heat transfer, where we can model heat transfer from thermal mixing if you have streams of different temperatures that are coming together. We have quite a few different heat exchanger options where we won't go through each here, but some are more theoretical, maybe specifying a stagnation enthalpy rise or heat rate in, or fixing the temperature and letting the heat rate float, or modeling the actual heat exchanger conditions like counterflow, crossflow, parallel heat exchangers. You can thermally link heat exchangers. So let's say you have 2 different fluids, or maybe you're recycling heat within your system. You can link those together. And again, it'll use the hydraulics to determine how much heat rate is going to be transferred from one to the other. There's also ambient heat exchange, which you can specify for your piping, adding things like insulation, creating a resistance network, conducting through the pipe, through the insulation, and then the convection both outside and inside the pipe. Before we wrap up, we'll touch on add-on modules where we have 4 available. The first is goal seek and control, where you can automate any iterative processes. You can set a variable within your model, like valve position or pipe scaling, until it's able to achieve a goal. Extended time simulation, which uses a series of steady state snapshots to model long transients. For example, we could calculate how much mass is removed from a tank within 1 second. That then determines how much water is left in the tank, what's your new tank level, what's your new approximate steady state. The settling slurry module is useful if you are transporting solids within your fluid or using fluids as a carrier fluid, accounting for things like the additional pressure losses and determining whether or not the solids in your system will settle out. And the final module is the automated network sizing module, which will test different pipe diameters for you to minimize things like weight, capital cost, or life cycle cost as well. Note what we talked about today is AFT Fathom, which again is our liquid steady state tool, but we can also model those slow transients like tank filling or tank draining, rapid transients for water hammer analysis or surge analysis, and then also pulsation in those liquid systems. We have similar complementary products for gas and steam. One thing that I like to note in doing these presentations is that all of the skills, everything that we touched on today in learning Fathom will immediately translate to Impulse, Aero, and Extreme. So all of these scenario cases, the idea of pumps, pipes, and junctions, all the library cases, fluid libraries, again, all of that translates across all of the different products. If you're looking to learn more, if you're a new user, I'd recommend reviewing our Quick Start guide. We also have Quick Start videos on our website, which go through most of what we talked about today. How do you define your model? How do you specify fluids, adding pipes and junctions, making graphs? Again, if you are looking for a different presenter, maybe you can go and check out those Quick Starts, or it's a very easy reference for brand new users. If you like webinars, which I imagine you do, if you've stuck around through this one for the little more than an hour that we have been going, we do host webinars twice a month, and you can always access our backlog either from our website or from our YouTube channel. The webinars aren't necessarily introductory. In a lot of cases, we try to tackle more technical concepts. So pump concepts, maybe parallel pumps, what is a pump curve, how do you read a pump curve, check valve slam, why does it occur, how do you address it, compressibility effects or non-Newtonian fluids. Again, we try to emphasize the technical aspects of using the software, not just purely instructional. You can also find all of our documentation online from docs.aft.com. That's useful for specific equations or theory, or if you're looking for additional example files to work through. There's a range of other resources we won't go into full depth on. The main ones I would touch on is our training seminar, which we do host 3 times per year here in our office in Colorado Springs, but we can also provide training seminars on site if you have enough engineers to justify sending an instructor out. Tips and tricks blogs, those are posted once a month, and then also other technical papers, white papers, articles that you can use to hopefully build better models or representations of your system. The last thing I'll touch on is if you have an active support upgrade and maintenance subscription, or if you are leasing our software, you have access to our support team of engineers. They're either based in the US here, or if you are one of our international customers, you can contact our local channel partner for support as well. We also sell what's called a Flow Expert package. If you have more complex questions that go beyond the scope of support, you can purchase a package of ours to work with an engineer. We can review your model, your results, or teach you some of the more fundamental modeling concepts. If you want to completely hand off a hydraulic project, you can work with our consulting group, Purple Mountain Technology Group, and this is a sister company to AFT, most often looking at water hammer analysis, but also just more typical steady state analysis, compressible flow, again, anything that you can model within our applications. So that's the most formal. We would issue a proposal, talk through the scope of the project, and then provide a report and likely a final model. So it's a lot of content to jump in. What I think is interesting is we're really only scratching the surface with this introduction, but let's go through and talk about what we learned today. First, AFT Fathom is a steady state incompressible internal flow analysis tool. So we're looking at piping systems, pumps, components, things of that nature. But we also have other offerings for compressible and transient flow analysis. Everything that we looked at today is going to quickly translate into those other applications. So if you have a compressible project that comes up, if you are a competent Fathom user, again, all of those skills will translate to an AFT Aero project. We reviewed the model process in two parts, really. The first being model building, looking at the workspace and model data to input all of our properties and then double check them before we perform our analysis. Where within analysis, we can look at output for tabulated information, graph results for profile graphs and pump versus system graphs, and then also using workspace layers to associate our input and output with our objects or to color code it based on those parameters. As I mentioned, this introduction is really only scratching the surface of what AFT Fathom has to offer. We looked at a lot of different resources that are available for you to refine your own skills. And then again, if you really want the most complete training that we offer, we do have 2-day training seminars where we talk about nothing but Fathom, go through each of the components in more detail. How do you approach building a system? What's good modeling practices? Things like that. And again, if you do have active support, we love helping engineers using our software. And we really pride ourselves on that customer support aspect. So hopefully you learned something new, especially if you're a brand new user. I'm sure there's a lot of things that you can now take with you in building your first model. And if you're a more experienced user, hopefully there were some tips and tricks that you can incorporate into your own workflow. If you have any remaining questions, feel free to send an email to webinars@aft.com. And if you have any topics for future webinars, again, we try to do 2 per month, so we're always looking for new topics. That too, you can submit to webinars@aft.com. Again, my name is Nick Vastine, Business Applications Engineer here with AFT. Especially if you've made it to the end of the webinar, hopefully it's created some value for you, and we look forward to having you in the next AFT webinar sometime soon. Have a nice rest of your day. And of course, we hope to see you again soon. Thanks.